Because of the strong nuclear force, the nucleons in a stable nucleus, which are protons and neutrons, are held tightly together. The amount of energy required to remove nucleons from a nucleus is called binding energy. The more stable the nucleus is, the greater is the amount of energy needed to break it apart. We can link this concept of binding energy to the world-famous mass-energy equivalence formula, which is E equals mc squared, by calculating the mass defect of a nucleus. The mass defect is the difference between the mass of the nucleus and the sum of the masses of its individual nucleons. An example of this can be found when calculating the mass of helium by summing up the masses of each individual nucleon and comparing that to the actual mass measured experimentally. To calculate the mass defect, what we need is the masses of the individual protons and neutrons. Here we're going to calculate the mass defect of a helium nucleus, which we know has two protons and two neutrons. So to get the number, we're going to have to multiply the mass of the proton by 2, as well as the mass of the neutron, and then sum them up to obtain the total mass of its individual nucleons. And we know that experimentally, the helium mass has been calculated to be this number here. So when we subtract the calculated mass to the actual mass of helium, we get this number here, which is very small but is equivalent to the difference of the sum of its nucleons and the actual value of its mass. Once we have the mass defect, the binding energy can be calculated by using the mass energy equivalence formula. This time, binding energy equals mass defect times speed of light squared.
Once we obtain the mass defect, we can calculate the binding energy with the following formula, which is the Einstein's classic formula of energy equal mass times speed of light squared. So we multiply the mass defect times the speed of light squared, and we obtain this energy in joules over nucleus. It seems small, but once you apply it to the whole mole of helium, you obtain a very large energy, joules per mole.
Binding energy is basically where nuclear energy comes from when a process called fission takes place. Fission is a process in which a large nucleus splits into two lighter ones. It would be amazing to obtain such amounts of energy like in the example from the splitting of nuclei. But for this to happen in real life, the nucleus needs to have a certain level of instability to make the actual process of separation of nucleons possible. As elements get very large, the proton electron repulsion effect becomes stronger, and to be stable, a nucleus needs extra neutrons to overcome this repulsion. However, when the number of protons reaches 89, there can no longer be enough neutrons in the nucleus, which makes it unstable. An unstable atom seeks to reach equilibrium between nucleons through radioactive decay, which is what nuclear physicists take advantage of when using uranium-235 in nuclear power plants. The reason as to why mostly uranium is used in these plants is that it is the only fissile element that is widely found in nature.
As said before, nuclear fission occurs when a very heavy nucleus such as uranium-235 splits, or fissions, into two particles of comparable mass. In such a reaction, the total mass of the product particles is less than the original mass. Fission is initiated by the capture of a thermal neutron by a heavy nucleus and involves a release of about 200 MeV per fission. This energy release occurs because the smaller fission product nuclei are more tightly bound by about 1 MeV per nucleon than the original heavy nucleus. The fission of uranium-235 by thermal neutrons can be represented by the equation below. In this equation, one thermal neutron combines with uranium-235. Then this uranium, by absorbing the neutron, becomes uranium-236, and this uranium is in its excited state. This means that it is unstable and will then split into two particles and some neutrons. The resulting nuclei X and Y are called fission fragments. There are many combinations of X and Y that satisfy the requirements of conservation of mass energy, charge, and nuclear number. This figure shows the actual mass distribution of fragments in the fission of uranium-235, being the most probable around mass number 90 and 140. On the average, about 2.5 neutrons are released per event. A typical reaction of this type is the following. One neutron combining with uranium-235 give as a result the isotope of barium of 141 and the isotope of krypton 92 plus 3 neutrons. Of the 200 megaelectron volts or so released in this reaction, most goes into the kinetic energy of the heavy fragments barium and krypton. The breakup of the uranium nucleus can be compared to what happens to a drop of water when excess energy is added to it. All the atoms in the drop have energy, but not enough to break up the drop. However, if enough energy is added to set the drop into vibration, it undergoes elongation and compression until the amplitude of vibration becomes large enough to cause the drop to break. In the uranium nucleus, a similar process occurs. So, the steps for fission are the following. 1. The uranium-235 nucleus captures a thermal or slow-moving neutron. This capture, then, results in the formation of uranium-236, and the excess energy of this nucleus causes it to undergo violent oscillations. The uranium-236 nucleus becomes highly distorted, and the force of repulsion between protons in the two halves tend to increase the distortion. The nucleus splits into two fragments, emitting several neutrons in the process. Since fragments that have a large excess of neutrons are unstable, the neutron-rich fragments almost instantaneously release 2 or 3 neutrons. The remaining fragments are still rich in neutrons and proceed to decay to more stable nuclei through a succession of beta decays. Now let's do some math.
So now we're going to analyze an example of how many energy is lost in the process of a nuclear fission reaction. So first we have an uranium nuclei, and it is going to be affected by an external force, in this case 1 neutron. So when it collides with it gives us 2 elements, in this case barium and krypton, and that 2 elements release 3 neutrons. So we're going to make an example analyzing the reaction made in this process. So we have 1 neutron and 1 plus 1 uranium. It gives us barium, krypton, and the 3 new neutrons and the energy that was lost in the process. So we first have to calculate the mass defect. So we have the masses of each element in atomic unit mass. So we sum each side of the equation, that is neutron plus uranium, and in the other side is barium, krypton plus the 3 masses of the neutrons. So this defect mass gives us the value of 0.185733 in unit masses. So to calculate the energy, we have to convert that unit into megaelectron volts. So we only multiply this mass and by 931.5 megaelectron volts, and that gives us the energy of 173.701 megaelectron volts.
As mentioned before, a nuclear fission reaction can be represented by the following equation. However, if we want to apply this reaction into a nuclear reactor, we have 2 problems. 1, the neutrons that are emitted during the fission are high energy neutrons. This means that they go through a very high velocity. However, for the nuclear fission to occur, we need thermal neutrons. These neutrons have to be slow-moving neutrons. The second issue we have is that after every iteration, we end up having 2.5 neutrons. If these 2.5 neutrons then interact with other uranium atoms, we will have what is called a chain reaction. However, we will have an unstable chain reaction since the amount of uranium fissioning will increase exponentially and this will cause an explosion. A nuclear reactor is a system that maintains a self-sustained chain reaction. This means that after each iteration, on average, 1 neutron is produced, not 2.5. The ideal design for a nuclear reactor will be the following. A concrete wall will need to be installed so that it surrounds the reactor core, or where the fission is taking place. A very thick concrete wall is needed, since the reaction produces radioactivity due to the beta decay of the fission fragments. The next thing it has to have is the nuclear fuel, which in this case will be uranium rods. These rods are composed of about 99% of uranium-238 and the rest uranium-235. Surrounding the rods will be water, which will act as a coolant. This water will be put into the system as cold water and will exit the system as steam. This steam will then go through a heat exchanger which will power some turbines and as a result produce electrical energy. Now we need to solve the two issues mentioned before. To slow the neutrons down, we can use classical mechanics to find the solution. During the collision, we assume that momentum and kinetic energy are conserved. Therefore, after some mathematical manipulation, we find that the mass of the particle that the neutron is colliding with has to be about the same mass as the neutron. A proton has about the same mass as the neutron. We can find protons in hydrogens, and these hydrogens can be found in water. Lucky enough, our coolant also acts as a moderator as it allows the neutrons to slow down. To solve our second issue, nature will help. The first thing it helps us with is with uranium-238. Uranium-238 absorbs some neutrons, but no fission takes place. Since it does not fissions from its excited state, it will fall back to its ground state, emitting a gamma photon. Ether is then the proportion that survives not being absorbed. However, if the neutrons are fast enough, there is a very low probability that it would indeed fission, which will produce more neutrons. Epsilon are then the neutrons produced by this fissioning. The third thing to take into account is the fact that if the neutrons have an energy between 1 and 100 electron volts, there is a probability that they are absorbed due to resonance, but no fission takes place. P is then that proportion that survives this absorption. The fourth and final thing is the fact that water can also absorb neutrons, transforming first into deuterium and then into tritium. F is then the proportion that survives this absorption. The letter K is then used to represent the number of neutrons left after each iteration, taking into account the previous factors. Now, is it really important that K equals 1? To answer that, we will see what will happen if K is slightly greater than 1. So K equals 1 plus lambda, lambda can be any value, and tau will represent the time between iterations. Tau is the time it takes for a neutron to be emitted and then to reach another uranium and start another fission process. For us, and in general, this time equals about 0.1001 second. So after time t, we will have t over tau iterations. And to know how many neutrons we have after that many iterations, we'll write the following equation. Now, if we apply natural log on both sides, we find that natural log of 1 plus lambda is approximately lambda if lambda is small enough. So, as our final equation, we have that the number of neutrons after a time t will be the number of neutrons at the beginning times e to the t lambda over tau. Now let's see how many neutrons we will have after 1 second. So if t equals 1 second, and we take lambda about 0.01, we find that the number of neutrons after 1 second is the number of neutrons at the beginning times e to the 10. E to the 10 is approximately 22,026. So after 1 second, we will have 22,026 times the number of neutrons we had at the beginning, and that is a very large number, and it will ultimately explode and we have an explosion. So as we could see, if K is slightly greater than 1, about 1%, we will have too many neutrons. In real life, in a nuclear reactor, they try to have these many neutrons. However, how do they control it? We control it through cadmium rods. Cadmium rods are great neutrons absorbers.
Although there are several types of reactor that convert the kinetic energy of fission fragments to electrical energy, the most common type in use in the United States is the pressurized water reactor. Its main parts are common to all reactor designs. Fission events in the reactor core supply heat to the water contained in the primary closed loop, which is maintained at high pressure to keep it from boiling. This water also serves as a moderator. The hot water is pumped through a heat exchanger, and the heat is transferred to the water contained in the secondary loop. The hot water in the secondary loop is converted to steam, which drives a turbine-generated system to create electric power.
Nuclear reactors and nuclear energy come along with a lot of advantages and disadvantages that enter to the debate of whether to use or not to use this kind of energy. Some of the advantages of nuclear energy are the following. The cost of nuclear energy are relatively low compared with other forms of energy. It provides a stable load of energy and it's a high energy density resource. It works with our distribution network, which means we do not have to create a new one. And the pollution emitted to the environment is relatively low. It supports of greatest power needs. On the other hand, some of the disadvantages of nuclear energy are the following. It requires a large infrastructure and waivers are often required for communities to use nuclear energy, which means that the investment cost is going to be large. It produces radioactive waste, which means that the environment can be harmed.
Tried to break love to science in an act of good defiance.